Pronounced a star is a graph traversal and pathfinding algorithm that is used in many fields of computer science due to its completeness, optimality, and optimal efficiency. Given a weighted graph, a source node and a goal node, the algorithm finds the shortest path with respect to the given weights from source to goal. One major practical drawback is its OBD OBD space complexity, where D is the depth of the shallowest solution, the length of the shortest path from the source node to any given goal node, and B is the branching factor, the maximum number of successors for any given state, as it stores all generated nodes in memory. Thus, in practical travel routing systems, it is generally outperformed by algorithms that can preprocess the graph to attain better performance, as well as by memory-bounded approaches. However, * is still the best solution in many cases. Peter Hart, Nils Nilsson, and Bertram Raphael of Stanford Research Institute Nausri International first published the algorithm in 1968. It can be seen as an extension of Dijkstra's algorithm. * achieves better performance by using heuristics to guide its search. Compared to Dijkstra's algorithm, the algorithm only finds the shortest path from a specified source to a specified goal, and not the shortest path tree from a specified source to all possible goals. This is a necessary trade-off for using a specific goal-directed heuristic. For Dijkstra's algorithm, since the entire shortest path tree is generated, every node is a goal, and there can be no specific goal-directed heuristic. History. * was created as part of the Shaky project, which had the aim of building a mobile robot that could plan its own actions. Nils Nilsson originally proposed using the graph traverser algorithm for Shaky's path planning. Graph traverser is guided by a heuristic function hn, the estimated distance from node n to the goal node. It entirely ignores gn, the distance from the start node to n. Bertram Raphael suggested using the sum gn plus hn. Peter Hart invented the concepts we now call admissibility and consistency of heuristic functions. * was originally designed for finding least cost paths when the cost of a path is the sum of its costs, but it has been shown that * can be used to find optimal paths for any problem satisfying the conditions of a cost algebra. The original 1968 * paper contained a theorem stating that no * like algorithm A could expand fewer nodes than * if the heuristic function is consistent, and * tie-breaking rule is suitably chosen. A correction was published a few years later claiming that consistency was not required, but this was shown to be false in 1985 in Dechter and Perl's definitive study of AS optimality, now called optimal efficiency, which gave an example of a * with a heuristic that was admissible but not consistent, expanding arbitrarily more nodes than an alternative * like algorithm. Description. * is an informed search algorithm, or a best first search, meaning that it is formulated in terms of weighted graphs, starting from a specific starting node of a graph. It aims to find a path to the given goal node having the smallest cost, least distance traveled, shortest time, etc. It does this by maintaining a tree of paths originating at the start node and extending those paths one edge at a time until the goal node is reached. At each iteration of its main loop, * needs to determine which of its paths to extend. It does so based on the cost of the path and an estimate of the cost required to extend the path all the way to the goal. Specifically, * selects the path that minimizes fn equals gn plus hn, \fn equals gn plus hn, where n is the next node on the path, gn is the cost of the path from the start node to n, and hn is a heuristic function that estimates the cost of the cheapest path from n to the goal. The heuristic function is problem-specific. If the heuristic function is admissible, meaning that it never overestimates the actual cost to get to the goal, * is guaranteed to return a least cost path from start to goal. Typical implementations of * use a priority queue to perform the repeated selection of minimum estimated cost nodes to expand. This priority queue is known as the open set, fringe, or frontier. At each step of the algorithm, the node with the lowest f(x) value is removed from the queue. The f and g values of its neighbors are updated accordingly, and these neighbors are added to the queue. The algorithm continues until a removed node, thus the node with the lowest f value out of all fringe nodes is a goal node. The f value of that goal is then also the cost of the shortest path, since h at the goal is 0 in an admissible heuristic. The algorithm described so far only gives the length of the shortest path. To find the actual sequence of steps, the algorithm can be easily revised so that each node on the path keeps track of its predecessor. After this algorithm is run, the ending node will point to its predecessor, and so on, until some node's predecessor is the start node. As an example, when searching for the shortest route on a map, hx might represent the straight line distance to the goal, since that is physically the smallest possible distance between any two points. For a grid map from a video game, using the taxicab distance or the Chebyshev distance becomes better depending on the set of movements available for way or h-way. If the heuristic h satisfies the additional condition hx is less than or equal to dx, y plus hy for every edge x, y of the graph where d denotes the length of that edge, then h is called monotone, or consistent. With a consistent heuristic, asterisk is guaranteed to find an optimal path without processing any node more than once, and asterisk is equivalent to running Dijkstra's algorithm with the reduced cost dx, y equals dx, y plus hx. Pseudocode. The following pseudocode describes the algorithm. Function reconstruct underscore path came from current. Total underscore path equals current, while current in came from keys. Current equals came from current. Total underscore path dot prepend current. Return total underscore path. A asterisk finds a path from start to goal. Per hour is the heuristic function. Hn estimates the cost to reach goal from node n. Function a underscore star start. Goal h, the set of discovered nodes that may need to be re-expanded. Initially, only the start node is known. This is usually implemented as a min heap or priority queue rather than a hash set, open set, start. For node n, came from n is the node immediately preceding it on the cheapest path from the start. To n currently known, came from, equals an empty map. For node n, core n is the currently known cost of the cheapest path from start to n. Core equals map with default value of infinity. Core start equals 0. For node n, score n, core n plus hn. Score n represents our current best guess as 2. How cheap a path could be from start to finish if it goes through n. Score equals map with default value of infinity. Score start, h start. While openset is not empty, this operation can occur in olog in time if openset is a min heap or a priority queue. Current equals the node in openset having the lowest score value. If current equals goal, return reconstruct underscore path came from current. Openset, remove current. For each neighbor of current, dcurrent, neighbor is the weight of the edge from current to neighbor. Tentative underscore core is the distance from start to the neighbor through current. Tentative underscore core equals core current plus dcurrent, neighbor. If tentative underscore core less than core neighbor, this path to neighbor is better than any previous one recorded. Came from neighbor, current, core neighbor, tentative underscore core. Score neighbor, tentative underscore core plus h neighbor. If neighbor not in openset, openset.add neighbor. Openset is empty but goal was never reached, return failure. Remark, in this pseudocode, if a node is reached by one path, removed from openset, and subsequently reached by a cheaper path, it will be added to openset again. This is essential to guarantee that the path returned is optimal if the heuristic function is admissible but not consistent. If the heuristic is consistent, when a node is removed from openset the path to it is guaranteed to be optimal, so the test tentative underscore core less than core neighbor will always fail if the node is reached again. The pseudocode implemented here is sometimes called the graph search version of ***. This is in contrast with the version without the tentative underscore core less than core neighbor test to add nodes back to openset, which is sometimes called the tree search version of ** and require a consistent heuristic to guarantee optimality. Example: an example of an A algorithm in action where nodes are cities connected with roads and hx is the straight line distance to the target point, key, green, start, blue, goal, orange, visited. The asterisk algorithm has real-world applications. In this example, edges or railroads and hx is the great circle distance, the shortest possible distance on a sphere to the target. The algorithm is searching for a path between Washington, D.C. and Los Angeles. Implementation details. There are a number of simple optimizations or implementation details that can significantly affect the performance of NA implementation. The first detail to note is that the way the priority queue handles ties can have a significant effect on performance in some situations. If ties are broken so the queue behaves in a LIFO manner, asterisk will behave like depth-first search among equal cost paths, avoiding exploring more than one equally optimal solution. When a path is required at the end of the search, it is common to keep with each node a reference to that node's parent. At the end of the search, these references can be used to recover the optimal path. If these references are being kept, then it can be important that the same node doesn't appear in the priority queue more than once, each entry corresponding to a different path to the node, and each with a different cost. A standard approach here is to check if a node about to be added already appears in the priority queue. If it does, then the priority and parent pointers are changed to correspond to the lower cost path. A standard binary heap-based priority queue does not directly support the operation of searching for one of its elements, but it can be augmented with a hash table that maps elements to their position in the heap, allowing this decreased priority operation to be performed in logarithmic time. Alternatively, a Fibonacci heap can perform the same decreased priority operations in constant amortized time. Special cases. Dijkstra's algorithm, as another example of a uniform cost search algorithm, can be viewed as a special case of a asterisk where h(x) equals 0, hx equals 0 for all x. General depth-first search can be implemented using asterisk by considering that there is a global counter C initialized with a very large value. Every time we process a node, we assign C to all of its newly discovered neighbors. After every single assignment, we decrease the counter C by 1. Thus, the earlier a node is discovered, the higher its hx hx value. Both Dijkstra's algorithm and depth-first search can be implemented more efficiently without including an hx hx value at each node. Properties, termination and completeness. On finite graphs with non-negative edge weights, asterisk is guaranteed to terminate and is complete, i.e. it will always find a solution, a path from start to goal if one exists. On infinite graphs with a finite branching factor and edge costs that are bounded away from 0, d, x, y, greater than, epsilon, 0. Textile dx, y greater than, if epsilon greater than 0 for some fixed, epsilon. Display style of epsilon, asterisk is guaranteed to terminate only if there exists a solution. Admissibility. A search algorithm is said to be admissible if it is guaranteed to return an optimal solution. If the heuristic function used by asterisk is admissible, then asterisk is admissible. An intuitive proof of this is as follows. Call a node closed if it has been visited and is not in the open set. We close a node when we remove it from the open set. A basic property of the algorithm, which we'll sketch a proof of below, is that when n, n is closed, if n, fn is an optimistic estimate lower bound of the true distance from the start to the goal. So when the goal node, g, g is closed, f, g, fg is no more than the true distance. On the other hand, it is no less than the true distance, since it is the length of the path to the goal plus a heuristic term. Now we'll see that whenever a node n, n is closed, fn, fn is an optimistic estimate. It is enough to see that whenever the open set is not empty, it has at least one node. N, display style n on an optimal path to the goal for which G, N, display style Gn is the true distance from start, since in that case G, N, display style Gn plus H, N, display style Hn underestimates the distance to goal, and therefore so does the smaller value chosen for the closed vertex. Let P, display style P be an optimal path from the start to the goal. Let P, display style P be the last closed node on P, display style P for which G, P, display style GP is the true distance from the start to the goal. The start is one such vertex. The next node in P, display style P has the correct G, display style G value since it was updated when P, display style P was closed, and it is open since it is not closed. Optimality and consistency. Algorithm is optimally efficient with respect to a set of alternative algorithms alts on a set of problems P if for every problem P in P and every algorithm in alts. The set of nodes expanded by in solving P is a subset possibly equal of the set of nodes expanded by in solving P. The definitive study of the optimal efficiency of a * is due to Rena Dechter and Judea Pearl. They considered a variety of definitions of alts and P in combination with the asterisks heuristic being merely admissible, or being both consistent and admissible. The most interesting positive result they proved is that asterisk, with a consistent heuristic, is optimally efficient with respect to all admissible asterisk-like search algorithms on all non-pathological search problems. Roughly speaking, their notion of the non-pathological problem is what we now mean by up to tie breaking. This result does not hold if A's heuristic is admissible but not consistent. In that case, Dechter and Pearl showed there exist admissible asterisk-like algorithms that can expand arbitrarily fewer nodes than asterisk on some non-pathological problems. Optimal efficiency is about the set of nodes expanded, not the number of node expansions, the number of iterations of a asterisk's main loop. When the heuristic being used is admissible but not consistent, it is possible for a node to be expanded by a asterisk many times. An exponential number of times in the worst case. In such circumstances, Dijkstra's algorithm could outperform a asterisk by a large margin. However, more recent research found that this pathological case only occurs in certain contrived situations where the edge weight of the search graph is exponential in the size of the graph, and that certain inconsistent but admissible heuristics can lead to a reduced number of node expansions in A searches. Bounded relaxation. While the admissibility criterion guarantees an optimal solution path, it also means that asterisk must examine all equally meritorious paths to find the optimal path. To compute approximate shortest paths, it is possible to speed up the search at the expense of optimality by relaxing the admissibility criterion. Oftentimes we want to bound this relaxation so that we can guarantee that the solution path is no worse than 1 plus epsilon times the optimal solution path. This new guarantee is referred to as epsilon admissible. There are a number of epsilon admissible algorithms, weighted asterisk, static weightings. If Hn is an admissible heuristic function, in the weighted version of the A search one uses HW and equals epsilon Hn, epsilon greater than 1 as the heuristic function, and perform the asterisk search as usual, which eventually happens faster than using Ha since fewer nodes are expanded. The path hence found by the search algorithm can have a cost of at most epsilon times that of the least cost path in the graph. Convex upward, downward parabola XUP, XDP. Modification to the cost function in weighted asterisk to push optimality toward the start or goal. XDP gives paths which are near optimal close to the start, and XUP paths are near optimal close to the goal. Both yield A, display style, epsilon, optimal paths overall. Display style f underscore text xdpn equals frac 1 to epsilon left gn plus 2 epsilon minus 1 plus skirt gn hn to plus 4 epsilon gn hn right f zup n equals 1 2 a g n plus h n plus g n plus h n 2 plus 4 a 1 h n 2. Display style f underscore text xupn equals frac 1 to epsilon left gn plus hn plus skirt gn plus hn to plus 4 epsilon minus 1 hn to right. Piecewise upward, downward curve PWXU, PWXD. Similar to XUP, XDP but with piecewise functions instead of parabola. Solution paths are also a display style epsilon optimal. Display style f underscore text PWXDN equals begin cases gn plus hn and text if hn gn plus 2 epsilon minus 1 hn epsilon and text if hn let gn and cases. Display style f underscore text PWXUN equals begin cases gn to epsilon minus 1 plus hn and text if gn to epsilon minus 1 hn gn plus hn epsilon and text if gn ject to epsilon minus 1 hn and cases. Dynamic weighting uses the cost function f n equals g n plus 1 plus epsilon w n h n. Display style f n equals g n plus 1 plus for epsilon w n h n, where w n equals 1 d n and d n is less than or equal to n 0. Otherwise, display style w n equals begin cases 1 frac d n and d n lecken 0 and text otherwise n cases and where d n display style dn is the depth of the search and n is the anticipated length of the solution path. Sampled dynamic weighting uses sampling of nodes to better estimate and to bias the heuristic error. Epsilon display style underscore for epsilon asterisk. Uses to heuristic functions. The first is the focal list, which is used to select candidate nodes, and the second HF is used to select the most promising node from the focal list. Epsilon selects nodes with the function AF n plus BH F n. Display style AF n plus BH underscore FN, where A and B are constants. If no nodes can be selected, the algorithm will backtrack with the function CF n plus DH F n. Display style CF n plus DH underscore FN, where C and D are constants. Alpha asterisk attempts to promote depth-first exploitation by preferring recently expanded nodes. Alpha asterisk uses the cost function f alpha n equals 1 plus w alpha n f n. Display style f underscore alpha n equals 1 plus w underscore alpha n f n, where w alpha n equals lambda g pi n is less than or equal to g n tilde lambda. Otherwise, display style w underscore alpha n equals begin cases lambda and g pi n lec g tilde n lambda and text otherwise n cases, where lambda and lambda are constants with lambda is less than or equal to lambda. Display style lambda lec lambda pi n is the parent of n, and g is the most recently expanded node. Complexity. As a heuristic search algorithm, the performance of a asterisk is heavily influenced by the quality of the heuristic function h n textile hn. If the heuristic closely approximates the true cost to the goal, asterisk can significantly reduce the number of node expansions. On the other hand, A poor heuristic can lead to many unnecessary expansions. Worst case scenario. In the worst case, asterisk expands all nodes. N, textile n for which f n equals g n plus each n is less than or equal to c, textile f n equals g n plus h n, lex c asterisk, where c, textile c asterisk is the cost of the optimal goal node. Why can't it be worse? Suppose there is a node n, textile n in the open list with f n c, textile f and c asterisk, and it's the next node to be expanded. Since the goal node has f g o v l equals g g o l plus h g o l equals g g o v l equals c, textile f goal equals g goal plus h goal equals g goal equals c asterisk, and f n c, textile f and c asterisk, the goal node will have a lower f value and will be expanded before it, textile n. Therefore, asterisk never expands nodes with f n greater than c, textile f n c asterisk. Why can't it be better? Assume there exists an optimal algorithm that expands fewer nodes than c, textile c asterisk in the worst case using the same heuristic. That means there must be some node n, textile and such that f n c, textile f and c asterisk, yet the algorithm chooses not to expand it. Now consider a modified graph where new edge of cost epsilon, textile, or epsilon with epsilon 0, textile, or epsilon greater than 0 is added from n, textile into the goal. If f n plus epsilon c, textile f n plus for epsilon c asterisk, then the new optimal path goes through n, textile n. However, since the algorithm still avoids expanding n, textile n, it will miss the new optimal path, violating its optimality. Therefore, no optimal algorithm including asterisk could expand fewer nodes than c, textile c asterisk in the worst case. Mathematical notation. The worst case complexity of a asterisk is often described as O, B, D. Textile OBD, where B, displaystyle B is the branching factor and D, textile D is the depth of the shallowest goal. While this gives a rough intuition, it does not precisely capture the actual behavior of a asterisk. A more accurate bound considers the number of nodes with f n is less than or equal to c, textile f n, lex c asterisk, if epsilon, displaystyle of epsilon is the smallest possible difference in f, textile f, cost between distinct nodes, then a asterisk may expand up to o, c, epsilon, displaystyle o, left, frac c asterisk, for epsilon, right. This represents both the time and space complexity in the worst case. Space complexity. The space complexity of a asterisk is roughly the same as that of all other graph search algorithms, as it keeps all generated nodes in memory. In practice, this turns out to be the biggest drawback of the asterisk search, leading to the development of memory-bounded heuristic searches, such as iterative deepening asterisk, memory-bounded asterisk, and SMA asterisk. Applications. Asterisk is often used for the common pathfinding problem in applications such as video games, but was originally designed as a general graph traversal algorithm. It finds applications in diverse problems, including the problem of parsing using stochastic grammars in NLP. Other cases include an informational search with online learning. Relations to other algorithms. What sets an asterisk apart from a greedy best-first search algorithm is that it takes the cost, distance already traveled, (GN), into account. Some common variants of Dijkstra's algorithm can be viewed as a special case of an asterisk where the heuristic hn equals 0, displaystyle hn equals 0 for all nodes. In turn, both Dijkstra and asterisk are special cases of dynamic programming. I asterisk itself is a special case of a generalization of branch and bound. I asterisk is similar to beam search except that beam search maintains a limit on the numbers of paths that it has to explore. Variance: anytime a asterisk, block a asterisk, d asterisk, field d asterisk. Fringe: fringe saving a asterisk fsa asterisk, generalized adaptive asterisk gaa asterisk. Incremental heuristic search, reduced to asterisk 33. Iterative deepening asterisk ida asterisk. Jump point search, lifelong planning asterisk lpa asterisk. New bidirectional asterisk in b asterisk. Simplified memory bounded asterisk SMA asterisk, theta asterisk. I asterisk can also be adapted to a bidirectional search algorithm, but special care needs to be taken for the stopping criterion. 35. See also, any angle path planning, search for paths that are not limited to moving along graph edges but rather can take on any angle. Breadth first search, depth first search. Dijkstra's algorithm, algorithm for finding shortest paths. Notes: asterisk-like means the algorithm searches by extending paths originating at the start node one edge at a time, just as asterisk does. This excludes, for example, algorithms that search backward from the goal or in both directions simultaneously. In addition, the algorithms covered by this theorem must be admissible, and not more informed than asterisk. Goal nodes may be passed over multiple times if there remain other nodes with lower f values, as they may lead to a shorter path to a goal.